Now we have seen that the capacitance of a parallel plate capacitor is given by epsilon naught A by D, and when we have discussed also that the particular capacitor has got certain limitations for its capacity, epsilon naught A upon D. So we have to increase the area, decrease the distance between the plates, and still they have practical limitations. We cannot have more area than a standard one, because ultimately this capacitor has to fit in some circuit. So we have to have a small area. So what do we do to increase the capacitance? One of the common features is to have the parallel combination of various capacitors. What is meant by a parallel combination? In parallel combination, what we mean is that the potential is same applied. The terminals of the capacitor are equally joined to a particular terminal of the battery, and the other terminals are equally joined to the other terminal of the battery. You can have a look at this type of combination. You can see there are three capacitors, C1, C2 and C3, all having the positive charge Q1, Q2 and Q3 are joined together, and they are connected to the battery positive terminal, and minus Q1, minus Q2, minus Q3 are the charges due to the battery terminal negative, and they are all joined together. So when we say the positive are this wire, this and this, they are all connected together, and these three wires are connected together, then we can say it's a parallel combination. In such a combination, you can see we have to find the equivalent capacitance. Instead of three capacitors, if we have one single capacitance, what's going to be its value? So now we go for it. We should understand that in such a case, we have to derive an expression for the equivalent in the figure. So we'll try to find the charges at all the capacitors individually. Since all the capacitors are connected to the voltage V, the charges will be Q1 will be equal to C1V, Q2 will be equal to C2V, and Q3 will be equal to C3V. Since V is constant for all the three terminals, for all the three capacitors, and hence, but charges are different depending on Q1, Q2 and Q3. But the net charge in the system would be sum of these three charges. The total charge in this combination has been stored as Q1 plus Q2 plus Q3. We place the values. The final charge Q is equal to Q1 plus Q2 plus Q3. We place the value of Q1, Q2, Q3 from the previous equation and we put it there. Ultimately, our equation becomes C1 plus C2 plus C3 equal to V. Now imagine if I have a single capacitor which will have the total capacitance we want to calculate. The total charge, it should have Q1 plus Q2 plus Q3. So total charge upon total voltage, that will be C equivalent. So we get the total charge Q applied by the total potential difference V in the combination. So we take C equivalent, becomes Q by V, which comes out to be C1 plus C2 plus C3. That means you can say in this type of combination, all the capacitors are simply added up. But with this addition, you should remember that the net capacitance is going to be larger than the largest because they are all added up. So one must remember that in this case, the net capacitance is greater than the greatest. I add 1 to 1000, my net answer will be more than 1000 because I am adding something to the largest capacitor. That's what we have to understand. So that means in the parallel combination, the advantage with us is that we can increase the capacitance with the same battery and the net capacitance is added up. In the next lecture, we'll try to find the series combination. There's other type of combination, and after doing these combinations, we'll have certain mixed type of questions so that you can solve any circuit problems. Thank you.